Hello, my name is Segon Lee, who is a PhD student at UT Austin. Today, I will present our paper Dynamo, a new key-value store for disaggregated persistent memory. Persistent memory is a new storage class memory technology that has high performance close to DRAM. For example, Intel Optane DCPM provides only 3 times higher access latency than DRAM. Moreover, it is non-volatile, retaining data across power outage, and provides high capacity, up to 512 GB for a single DIMM-like SSD. Although PM is an attractive medium due to its high performance, it has much higher cost per gigabyte than conventional storage devices. So ensuring high utilization is critical for a cost-efficient PM deployment. For a cost-efficient PM deployment, disaggregated persistent memory has been gathering traction. By disaggregating PM and making it shared across computes over network, we can reap the benefits of increasing utilization and reducing total cost of ownership. Furthermore, by disaggregating PM from computes, we can scale distinct resources independently and can separate failure domains. For example, to increase PM storage space, we don't need to add computes and PM together. And the failure in a compute node does not propagate to DPM or other alive compute nodes. However, the DRAM-like latency of PM makes disaggregation challenging. It is because the network interconnect latency is much higher than PM latency. We have an interest in building a persistent key-value store for this DPM. An ideal DPM key-value store should be able to provide high common case performance despite high network cost to access DPM. Furthermore, to enjoy the architectural benefits of scaling independence and failure separation, it must be scalable and elastic, which means scaling the performance in proportion to the provisioned resources, as well as quickly reconfiguring resources in response to the dynamics in the applications. However, we observed previously proposed DPM key-value stores have architectural limitations in achieving all the 3 goals simultaneously. They basically applied system architectures used in conventional distributed systems to DPM and inherit their trade-off as it is. For example, ASIM MVM employs shared nothing architecture to build their key-value store. In the right side figure, it partitions data and metadata within DPM and assigns the exclusive ownership of each partition to each compute node. By doing so, they can provide a high performance and scalability by caching data without any consistency overheads across different partitions and by providing cached data locality. However, it results in low elasticity. It is because it requires expensive data reorganization upon closer reconfigurations, like changing the number of compute nodes. Another counterpart example is Clover. Clover employs shared everything as their base architecture. The right side figure shows its system architecture. It makes data, metadata, and ownership shared across compute nodes. Due to this total sharing, they can provide high elasticity, adding one removing compute nodes without data reorganization. However, it results in low performance and scalability due to the expensive data consistency overhead for the shared data and the lack of the cached data locality. As shown so far, prior DPM key-value stores sacrifice one of high common case performance, scalability, or lightweight reconfigurations for the other two. Thus, there's a need for a new DPM key-value store that achieves these three properties simultaneously. So, we present Dynamo, which is the first DPM key-value store simultaneously achieving all the three goals. Dynamo is designed by adopting partitioning and caching techniques from storage research community, but we tailor them for DPM specifically. With the full end-to-end implementations, we evaluate Dynamo and show up to 10x better performance at scale and better elasticity than the state of the art. This is the outline for the rest of my talk. We first describe our system architecture, ownership partitioning. Ownership partitioning is a hybrid architecture which takes both advantages of shared nothing and everything simultaneously on DPM. Our approach is to partition ownership across compute nodes while sharing data through DPM. The insight behind this approach is that the data and ownership can be an independent consideration owing to the disaggregated architectures, so they can be separated each other. In ownership partitioning, all the physical data and metadata are shared through DPM, but the ownership to access data is partitioned across compute nodes. It allows fast reconfiguration without data reorganization by sharing data and metadata. We only need to redistribute ownership across compute nodes and invalidate stale cached data upon a compute node addition or removal, which is much lighter than data reorganization in DPM. Furthermore, through the partitioned ownership, it ensures high performance and scalability by avoiding consistency overhead across compute nodes and preserving data locality of their caches in common cases. So based on this high-level system architecture, we now introduce our novel caching technique, disaggregated active caching. The number of network round trips to DPM is a dominant factor deciding the overall system performance. To reduce these round trips, caching data or metadata into compute nodes memory is very important. For a cache, we may consider caching either value or shortcuts into compute nodes memory. Caching value keeps the entire copy of DPM value into local memory. Shortcuts are the remote pointer to DPM, allowing compute nodes to directly access DPM data without metadata traversals. But they have different trade-offs. For example, when caching values, the compute nodes can access everything locally without round trips at caches, but it requires more cache space than shortcuts, causing higher capacity miss. However, we can get the value with one round trip at caches by caching shortcuts. As a shortcut is much smaller than a value, we can cache more key value pairs than value cache, reducing capacity miss rate. Caching values improve performance relative to caching shortcuts, but it requires more cache space. This can raise the following question. Is it better to cache a few values with no overhead on caches, or a larger number of shortcuts with fixed hit overheads? The answer is simple in extreme cases. In highly skewed workload, storing value is better. But when workloads are close to uniform distribution and their total size is larger than the cache, storing shortcut is better. Unfortunately, most workloads fall between these two extremes and offer no clear answer. The efficient ratio between value and shortcut can be dependent on workload patterns and available memory space. This motivates us to think an adaptive policy. Our disaggregated adaptive cache changes the ratio between value and shortcut entries using demotion and promotion. To be specific, by demoting value entry to shortcut at the eviction from the value cache, we increment the portion of the shortcut cache. The demotion captures the uniformity of the workload. For example, when a workload pattern is close to uniform, cache misses and evictions keep occurring. Then our caching policy keeps expanding the shortcut portion of the cache to reduce these cache misses. And we expand the portion of the value cache by promoting shortcut entry to value at the hit from the shortcut cache. This promotion reflects the skewness of the workload. We provide a specific promotion policy, taking into account the trade-offs from the promotion based on cache data entry size, hit cost, and miss cost. Based on this policy, we do this promotion only when the hit benefit from the promoted shortcut outweigh the aggregate miss cost of the evicted shortcut. So far, we have discussed our proposed partitioning and caching techniques. We now evaluate Dynamo. During the evaluation, we try to answer these questions in terms of performance, scalability, and elasticity. For the experiment, we use the following system configurations. For the baselines to compare, we use Clover for performance and scalability experiment, and for elasticity experiment, we use Dynamo N, which is a variant of Dynamo, to simulate shared nothing counterpart. For workloads, we use YTSP benchmarks. We first estimate the performance and scalability of Dynamo. This graph shows the performance and scalability result. Each x-axis indicates the performance, the number of compute nodes, and y-axis is its corresponding throughput. In this experiment, Dynamo scales to 16 compute nodes, while Clover does not beyond 4 compute nodes. With 16 compute nodes, Dynamo outperforms Clover up to 10x, showing the benefits of ownership partitioning and disaggregated adaptive caching. Next, we evaluate the elasticity of Dynamo. This graph shows our auto-scaling experiment, which scale compute nodes depending on the load variance. The x-axis presents the execution time, and y-axis indicates the corresponding throughput variance. In this experiment, we only observe a brief throughput dips in Dynamo at every reconfiguration. But Dynamo N experiences long throughput dips due to its expensive data reorganization overhead, showing the effectiveness of ownership partitioning at reconfigurations. To conclude, I presented Dynamo, which is the first key value store for DPM. Dynamo achieves a high performance, scalability, and elasticity simultaneously by adapting the novel combinations of ownership partitioning and disaggregated active caching. Evaluation results show Dynamo performs better than existing DPM key value stores. Our code is available on GitHub.